I study subduction zone processes. Subduction zones are where you have an oceanic plate that is being subducted underneath a lighter plate, and the largest earthquakes, the most destructive earthquakes, occur where the two plates meet. We also observe two different other types of behavior. We observe continuous creep, where the fault is always moving, and we also observe this type of behavior that's called slow slip. Slow slip is when you have movement along the fault that occurs over weeks to months to years, depending on where you're at in the world, and it moves at a much slower rate than traditional earthquakes. The thought is that they are increasing the stress on the section of the fault that generates these large earthquakes. In order to study the earthquakes that occur in subduction zones, we use data that's collected from seismometers on land, and we also use data that's collected from ocean bottom seismometers in order to capture earthquakes that are occurring along the subduction zone. I am focused on where earthquakes actually start. I'm particularly interested in the way different types of fault slip act together or against one another. And to do this, I look at observations. So I actually look at earthquakes themselves, and then I also model them using computer simulations. It produces these wonderful images and animations of the slip processes that are occurring that we can't actually see. So the model is very powerful in that way. A slow slip event propagates on the order of 10 kilometers a day. So the model allows you to see them in real time, but in just a few seconds, versus being able to wait 30 days to capture them using GPS or some sort of other tool. Not only that, but we get to look at the complexity of these slow slip events, which is something that we can't get from the observations, the complexity of them compared to traditional earthquakes. The models indicate that slow slip events increase the stress on the section of the fault in which large earthquakes start. It could be up to 100 times more during a slow slip event than when one is not occurring. So this suggests that one of these slow slip events could potentially trigger a large earthquake. I compare the results that I get from the models to the observations in order to understand if what the model produces, or the computer simulations produce, represents what we see in the real world. And if it does, ultimately we can use the results to understand the likelihood of the next great earthquake occurring.